The proposed concept of a pool reactor with a barometric cooling loop is a development of the simplicity and safety principle of the first trigger reactors and is based on equipment minimization and the use of passive systems. First of all, this refers to the heat removal system, which makes it possible to cool the core with a neutron flux level of more than 5 10 to the power of 14 neutrons per centimeter square per second. This possibility of obtaining high neutron fluxes is ensured by the intensification of the natural circulation of the heated coolant in the primary cooling circuit when it boils under low pressure conditions. The concept provides for the possibility of passive heat transfer from the primary circuit to the final heat sink, which can be atmospheric air. With normal natural circulation in the core of a pool reactor, for example, trigger reactors, even with a sufficiently deep immersion of the core, a relatively small difference in the densities of the heated and cold coolant in the reactor pool is provided. This does not make it possible to provide a high natural circulation driving head sufficient to create good conditions for heat removal from the fuel elements, for example, to prevent surface boiling in the core. In addition, the problem of the natural circulation of the coolant in the pool is that the rise of the coolant heated in the core to the water surface is accompanied by the release of radioactive gases into the reactor room. Therefore, most often these problems are solved by switching to forced circulation through the core, by extracting the coolant from the subzone space, thus creating a downward flow in the fuel assemblies. However, in this case, with a decrease in the forced flow rate, which leads to boiling in the fuel assembly, the heat removal conditions can deteriorate sharply, which creates risks of overheating and destruction of the fuel elements. The most optimal scheme for forced circulation of the coolant in the pool reactor is the scheme used in the opal reactor, which includes a stack with a side outlet for the heated coolant. For the case of natural coolant circulation in a pool reactor, such a scheme cannot be implemented, but it can be applied if a barometric circuit is used by raising the circulation pipelines above the pool. The proposed concept of a barometric reactor has its advantages, among which are the following. Ensuring the intensification of the natural circulation of the heated primary coolant when it boils under low pressure conditions created by the vacuum system. The concept provides for the possibility of passive heat transfer from the primary to the secondary circuit, in which atmospheric air can act as a refrigerant and ultimate heat sink. The design of the reactor plant is based on the priority of internal safety, and not engineering safety, based on the presence of many systems that come into operation in emergency situations. The reactor heat removal systems do not contain complex and expensive technical equipment that requires periodic repairs and maintenance. The reactor plant uses low enriched fuel, less than 20% uranium-235. Due to the peculiarities of the coolant circulation path in the primary cooling circuit, a minimum level of release of radioactive products from the water surface of the reactor pool is ensured. The upward direction of coolant movement in the core ensures the stability of natural circulation during power fluctuations. The simplicity of design and the minimum cost of engineering systems and structures determine the low cost of building a reactor plant and minimal costs during its decommissioning. The absence of pumping and other equipment with high power consumption in the cooling circuit increases the safety of the reactor plant. The range of possible applications of the barometric reactor corresponds to the global trends in increasing the use of reactors while maintaining all the requirements of nuclear and radiation safety. The concept proceeds from the fact that low costs for the construction of a reactor plant and a minimum amount of heat engineering equipment will allow them to be built into specialized industrial and medical complexes. For example, to ensure the production of radiopharmaceuticals in radiological centers, radiation doping of silicon for power semiconductor devices, and so on. A feature of the barometric circuit of natural circulation is that a significant increase in the driving pressure in the primary circuit is achieved due to the physical effect of the boiling of the coolant at reduced pressure in the upper part of the circulation circuit. This effect of the boiling up of a coolant can be illustrated by a simple physical experiment of boiling water at room temperature in the upper part of the vessel under vacuum. The conditions for the boiling of the coolant can be realized by raising the circulation loop above the water level in the reactor pool using circulation pipelines and using a vacuum system. The filling of the natural circulation barometric circuit is carried out under the influence of atmospheric pressure when a vacuum is created in the upper part of the circulation circuit connected to the vacuum system. In a filled circuit, When the coolant heated in the core rises above the water level in the reactor pool, its pressure in the pipeline decreases in proportion to the height above the water level in the pool. When the coolant with a temperature of 60 degrees Celsius rises to a height of 7.5 meters above the level in the pool, it reaches the saturation line and boils, reducing the average density of the coolant in the circulation pipeline. Because of this, the difference in the average densities of the coolant in the upper sections of the circulation pipeline increases sharply, which causes a multiple increase in the driving pressure of natural circulation. An increase in the temperature of the coolant at the outlet of the core with an increase in the power of the reactor leads to boiling at a lower altitude, and, accordingly, to an increase in the driving pressure and coolant flow in the primary circuit. Thus, there is a positive feedback between an increase in the reactor power and an increase in the coolant flow through the core, which is typical for natural circulation. The design of a vertical chimney located above the core, closed from above and having a side branch, ensures the lifting movement of the coolant in the fuel assemblies and the possibility of switching to the intrabasin circulation mode in the event of a failure of the vacuum system, and the termination of the coolant circulation in the barometric circuit. In this case, the reactor must be transferred to a subcritical state, and the intra-pool circulation circuit will ensure the safe removal of residual heat from the core. The combined use of the chimney design with a discharge pipeline and a boiling section in the upper part of the barometric circuit, as well as the presence of a passive system for switching to intrabasin circulation when the reactor cools down, ensure the simplicity and reliability of the heat removal system. To organize a partially isolated barometric circulation circuit, a cavity is created under the active zone, into which a cooled coolant is supplied. This cavity is directly connected to the core, so almost all incoming coolant is forced to pass through the core, except for a small fraction that is exchanged between the circulating coolant of the barometric circuit and the water of the reactor pool. For this purpose, a hole is made in the partition separating the cavity under the core and the reactor pool, through which mass transfer occurs between the circulation circuit and the pool, and through this hole the circulation pipelines are filled with coolant when the pipelines of the barometric circuit are evacuated. Through the same hole and the natural circulation valves in the chimney, a new natural circulation circuit is formed directly through the reactor pool if the circulation in the barometric circuit stops. With this design, even when switching to surface boiling on fuel elements, the system remains stable, since boiling in the core only intensifies the circulation through the fuel assemblies. By measuring the coolant flow in the barometric circuit, as well as its temperature at the inlet and outlet of the core, the thermal power of the reactor is quickly calculated. The sufficiently high pressure drop created across the core makes it possible to remove heat not only from fuel rods, but also from loaded irradiation devices in a neutron trap located in the center of the core. Although the primary circuit does not contain electrically dependent equipment and therefore does not require periodic maintenance and control, the presence of the second circuit can also complicate the operation of the reactor plant, especially if heat is removed by evaporative cooling, for example, cooling towers, spray ponds, etc. This is primarily due to the water treatment of the secondary circuit and the accumulation of hardness salts in the coolant, which impede the functioning of the heat exchanger. It should be remembered that when heat is removed in the secondary circuit by evaporation of water, about 1 ton of pure water will evaporate for each megawatt of the thermal power of the reactor, and all the salts contained in the cooling water of the secondary circuit will accumulate and partially deposit on the heat exchange tubes. This creates serious problems in the operation of the reactor plant. To solve the problems of water treatment and the problems of accumulation of hardness salts due to evaporation of distillate, the second circuit can be performed using dry cooling towers. However, in this case, in addition to dry cooling towers, pumps, shut-off and control valves, reliable power supply are required, and qualified maintenance of complex secondary circuit equipment. Due to the relatively small power of the reactor plant, the problem of heat removal from the primary circuit can be easily solved if atmospheric air is chosen as the coolant of the secondary circuit and, at the same time, the ultimate heat sink. A large diameter exhaust vent pipe can be used as the driving force for circulating outside air through the air heat exchanger, using the natural convection of the air heated in the heat exchanger. With such a design of the reactor cooling system, the control of the cooling air flow through the heat exchanger in order to maintain the predetermined temperature of the cooled coolant remains practically the only control element for heat removal from the reactor. This regulation can be carried out, for example, using unified louver-type air dampers with an electric drive. The heat removal system of the primary circuit of the reactor plant includes a core located in the pool, surrounded by a reflector, yellow. Above the active zone is placed a vertical pipe closed from above, chimney, with a side outlet of the heated coolant, pink. To average the temperature of the heated coolant, it passes through a mixer made in the form of a vertical pipe in a pipe, with inlets in the inner pipe distributed over a large height. In the upper part of the pipeline with the upward flow of the coolant, there is a section for the formation of steam. Further, the steam water flow is distributed over 4 air heat exchangers, where condensation and cooling take place. The cooled coolant enters the tank, from which it is sent through the pipeline, blue, to the lower part of the pool, to the chamber under the active zone. After heating in the core, the coolant enters the chimney, in the upper part of which there are valves for intrabasin circulation, and channels for the regulatory bodies of the control and protection system pass through the chimney cover. The key system for creating a barometric circuit is the vacuum system. This system ensures the rise of the coolant through the circulation pipeline above the water level in the pool. At the same time, a decrease in pressure in the lifting pipeline at a relatively high temperature of the coolant provides a boiling effect to create a natural circulation driving head. The evacuation system is connected to a tank into which the condensate is drained after cooling in heat exchangers. This makes it possible to ensure directed movement of the steam-water flow in air heat exchangers for condensation and cooling of the heat carrier. Non-condensable gases from the heat exchangers are also discharged into the same tank, and when the pressure in the tank rises, the vapor-gas mixture is discharged to the evacuated gas holder, which has a large volume and surface area. At the same time, the steam entering the gas tank condenses on the cold walls, and the condensate is drained through the drain pipe back into the tank with the cooled coolant. When the pressure in the gas tank increases, non-condensable gases are periodically pumped out by a small vacuum pump to the gas cleaning system. Thus, all radioactive gases formed in the core enter the gas holder, and most of them, having a short half-life, go into a safe state. The gases removed from the gas tank are cleaned through filters, which ensures the minimum release of radioactive substances into the environment. The barometric circulation circuit, during normal operation of the circuit, keeps radioactive gases from escaping into the reactor pool and further into the reactor room, therefore, it is a safety barrier. The transition of the reactor to a subcritical state causes a sharp decrease in thermal power. In this case, the operation of the barometric circuit may become unstable. Therefore, a transition is made from barometric to intrabasin natural circulation. This transition is made automatically, as the pressure in the chimney pipe rises and the hydrostatic pressure of the reactor basin ceases to press the discs of the natural circulation valves against the seating surface in the upper part of the chimney pipe. This leads to the formation of a new natural circulation loop with upward movement of the coolant in the core, when the colder coolant from the pool through the hole in the ceiling enters the subzone space, and the coolant heated in the core from the chimney pipe is discharged into the pool through the openings of the natural circulation valves. In addition to the advantages of the technological scheme with the use of a chimney to ensure the lifting movement of the coolant in the core, there are also disadvantages associated with access to fuel assemblies during their overload and with the operation of the operating elements of the control and protection system, since the drives for their movement are located above the reactor pool. This is due to the fact that the upper part of the chimney must be blocked to prevent bypassing the flow from the core. During the operation of the barometric circuit, the shutoff of the coolant flow through the upper part of the chimney is ensured by a tight fit of the cover to the end of the chimney. To ensure movement in the active zone of the operating elements of the control and protection system, holes for guide pipes are made in this cover, which do not interfere with the lifting of the cover for carrying out transport and reloading operations with fuel assemblies. The guide tubes themselves can either remain in place or also rise up, freeing the cell with the 5-tube VVR not fuel assemblies for reloading. Shutting off the flow through natural circulation valves, also located in the upper part of the chimney, is ensured by the excess of hydrostatic pressure in the pool over the pressure in the upper part of the chimney. This leads to the fact that the discs of natural circulation valves, freely suspended on cables, are tightly pressed against the seat of the holes on the side surface of the chimney during the operation of the barometric circuit. If this work stops, the forces holding the discs in the closed state disappear, they move away from the seats, creating an open natural circulation loop through the core directly in the reactor pool. The design of a pool-type research reactor with a barometric cooling circuit, using demineralized light water as a coolant and moderator, and metallic beryllium as a reflector, was chosen for the computational analysis. For an example of calculation, a core was chosen, formed from 24 8-tube fuel assemblies of the VVR-KN8 type and 6 5-tube fuel assemblies of the VVR-KN5 type with channels for the operating elements of the control and protection system, providing reactivity compensation, automatic control and emergency protection. A neutron trap with the maximum neutron flux density is located in the center of the active zone. The beryllium reflector can have horizontal and vertical channels for irradiation. It should be emphasized that the core and reflector can have any configuration required by the customer, based on the task set for such a reactor, as well as the availability of the selected fuel assembly type and reflector materials. The presented thermal hydraulic analysis relates, first of all, to the possibility of implementing a barometric scheme of the cooling circuit in a pool reactor. The analyzed reactor plant with a power of up to 12 megawatts has a completely passive two-loop heat removal system, the ultimate heat sink for which is atmospheric air. The direction of circulation of the coolant through the core is upward, therefore, a chimney closed from above with a side outlet is used. The absence of circulation pumps, shut-off and control valves and other mechanical equipment that can break down or fail makes such a system not only independent of power supply sources, but also fail-safe. The high intensity of natural circulation in the primary circuit through pipelines of large diameter makes it possible to provide a turbulent mode of coolant movement in the core with a high heat transfer coefficient from fuel elements. With a hydraulic diameter in the fuel assemblies of 4 mm, the heat transfer coefficient from the fuel element cladding to the coolant is over 10 kW per square meter per Kelvin, which provides good conditions for cooling the fuel assemblies. The hydraulic characteristic of the chosen configuration of the core with 30 fuel assemblies of the VVR-NOT type is shown in the graph. The flow rate of the coolant in the fuel assembly during heating in the core from 45 to 75 degrees is determined by the high driving pressure of natural circulation, corresponding to the low height of the onset of boiling of the hot coolant in the ascending flow of the pipeline, which causes a large difference in the average coolant densities in the ascending and descending pipelines of the circulation loop. This difference corresponds to the driving head of natural circulation exceeding 35 kilopascals, providing a coolant flow rate in the circulation circuit of about 350 cubic meters per hour at a coolant velocity in the core of about 1.5 meters per second. The flow rate and heating of the coolant correspond to a power of 12 megawatts. The computational analysis of the reactor plant was carried out using the computational thermal hydraulic code of the improved RELAP 5 estimate. Despite the fact that the reactor is a pool reactor, due to the design features of the reactor cooling circuit, the RELAP 5 thermal hydraulic code is very convenient for modeling natural coolant circulation processes. This code is based on a one-dimensional, two-fluid model of a steam-water mixture. The computational model makes it possible to consider and analyze the process of volumetric water boiling in the pipeline with a decrease in hydrostatic pressure with an increase in the height of the liquid rise. The nodalization scheme of the barometric circuit includes simple hydrodynamic components simulating the reactor pool, core, pipelines, vacuum vessel, and heat exchanger. The reactor plant model allows you to simulate the operating conditions of the reactor plant. A change in the thermal power of the core leads to a change in the parameters of natural circulation, which are calculated by the RELAP code, which makes it possible to analyze the operation of the reactor plant with non-stationary and stationary modes. For modeling hydrodynamic processes of natural circulation with volumetric boiling of the coolant due to a decrease in pressure in the upper part of the pipeline with an upward flow, it is very important that maps of two-phase flow regimes in vertical channels are programmed in the RELAP code. This allows you to simulate dynamic processes with a decrease or increase in the temperature of the heated coolant. Changes in the parameters of natural circulation in the barometric circuit were studied for the mode of reaching the reactor at a power of 12 megawatts and continuous operation at this power. The increase in power to 12 megawatts was carried out in steps of 2 megawatts for 2.5 hours. Achievable neutron flux density in a neutron trap exceeds 5 10 to the power of 14 neutrons per centimeter square per second. In the process of stepwise increase in power, the natural circulation mode was analyzed at various degrees of coolant cooling in the heat exchanger. Up to 20 degrees Celsius, up to 30 degrees Celsius, and up to 45 degrees Celsius. Heating of the coolant in the core in these modes can vary significantly depending on the flow rate of the coolant, which is determined by the driving pressure of natural circulation. The driving pressure is significantly affected by the correlation of the steam-water flow regime used in the RELAP code. The coolant flow boils as it rises to the upper part of the circulation loop, therefore, when switching from one flow regime to another, the calculated parameters of the driving head of natural circulation can change significantly, which affects the coolant flow through the core. The coolant flow through the core determines the fuel rod cooling mode and, depending on the heat transfer coefficient and the coolant temperature, the maximum temperature of the most heat-stressed fuel rod is determined. Calculation estimates show that when the core is in the pool at a depth of 10 meters and the boiling point of water rises to 120 degrees, there is no vaporization in the core. The analysis carried out using the RELAP 5 code shows the operability and efficiency of the barometric circuit, which makes it possible to simplify the cooling system of the pool reactor as much as possible and minimize the amount of heat engineering equipment that requires periodic maintenance, which increases dose loads on personnel. Sufficiently high neutron fluxes make it possible to efficiently produce irradiation in channels at minimal operating costs. So, the concept of a barometric reactor, despite its simplicity, can be used to develop promising research reactors that provide a solution to various problems of science and technology at minimal cost. As one of the many possible examples of the intended use of a barometric reactor, we can suggest its use in radiological centers to obtain molybdenum-99 radioisotopes, which is the basis for the creation of molybdenum-99/technetium-99 radioisotope generators, which are widely used in nuclear medicine for diagnostic purposes. The technology for obtaining activation molybdenum-99 is protected by a patent. At present, fission of the expensive uranium-235 is used in reactor plants to produce this radioisotope, with only a very small fraction of this nuclear fuel in the target being used before the target is sent for reprocessing to isolate the desired radioisotope, and 99% of the uranium-235 becomes high-level waste. Therefore, the application of the proposed activation method for obtaining molybdenum-99 will not only reduce the cost of its production, but also significantly reduce the amount of radioactive waste. At the same time, many other medical radioisotopes can be produced in the barometric reactor at the radiological center, which has a neutron source with a flux of 5 10 to the power of 14 neutrons per centimeter square per second. Another area of application for barometric reactors can be the production of nuclear-doped silicon in it, which is used to produce high-voltage power semiconductors, without which renewable energy is impossible. If we look at the electrical circuit of any solar or wind power plant, we will definitely see inverter equipment there, electrical machines that convert one direct current into another and into a network variable. They are needed for the dynamic organization of electricity flows inside a solar power plant or windmill and docking with the global power grid in the correct mode. Inverters, in turn, are a set of passive filters, working inductances and transformers, and most importantly, powerful electric switches. Relatively small semiconductor switches today have a maximum operating voltage of up to 7,000 volts at an operating current of up to 5,000 amperes, i.e. a device the size of a tea saucer is capable of switching 35 megawatts. Along with the highest efficiency in the region of 99% and relatively high switching frequency, such switches have largely defined the world of modern power electronics. Drives, electric motors, with high efficiency and flexible operation, such as drives for electric locomotives, Tesla electric vehicles or powerful machine tools. So, all semiconductor switches with operating voltages above 1,600 volts are made of silicon, which was irradiated in a nuclear reactor, nuclear-doped silicon. Currently, about 150 tons of such silicon per year is produced in 24 irradiators, usually based on research reactors. Producers are scattered all over the world, and the market size is approximately $150 million a year, and it is one of the largest global markets for isotope products. Thus, barometric reactors can become one of the locomotives of renewable energy sources, which makes them of particular importance.